Okay, hello everyone. I will keep it quick and I will just jump some parts. This is for general audience about what we call complexity. And so a complex system is emergent and it's adaptive and it's difficult to control, like the brain. On the other hand, a complicated system is fragile and easy to control, like a racket. So this is the difference. And to measure complexity, we use diffusion and entropy. And here I just demonstrate how we do that. Like imagine the blue curve is a signal we want to measure its complexity. So what we do, we define one threshold here, the white horizontal line, and then we see whenever the signal passes this threshold, we call that one event. And then that means we are interested in time intervals between the crossings. So we are looking for the temporal complexity of the signal. So then after we define all these events, then we can create the secondary time series, which is this one, the white. That is done by defining so at each event, there will be just one jump ahead. So, and this will give a step-like trajectory. And next step is we just define window size L, and then we cut this time series, this secondary time series, to pieces and bring all of them to start from 0. And of course, all of them will end up at length L. Then we can look at the distribution of these points. And by knowing the distribution, we can define entropy. And so this is a definition of Shannon entropy. And having P, we can define it. And if there is a scaling, and this is the definition of the scaling, just applying this function to the definition, we can by simple calculation see that entropy will be a constant based on window size L and the plus delta L logarithm of L. So just means
I'm sorry to interrupt you.
Yes?
Is there any way you can change the color of your blackboard from black to something else? Because we have, due to the projector colors and distortion, it's really hard to read.
Yeah, so no, I don't think. So when I write with red, you can see?
If you write in red, we can see. If you write it in blue or white, we don't see anything at all.
Okay, so this is not important because this is just the definition of entropy. Everyone knows that. So, but if we plug if there is a scaling, P of x of L will be equal to 1 over L power to delta. Delta is the scaling. F, which is a function, times x over L power to delta. So this means that x is proportional to L to delta. So then there's a scaling. And we are interested to this delta. And if you just plug this to the definition of entropy, easily you will find that SL is a constant, A plus delta, this is the parameter we are looking for, logarithm of window size L. That means if we plot entropy versus logarithm of window size, there will be a linear section that the slope of that linear part will give us the scaling of the process. So it's very easy tool to measure the complexity. Usually we use more than one stripe or threshold. Then this is like a signal, part of the EEG signal. So all these, whenever this trajectory passes one threshold to the other, like then we can define all these events. That gives us more of these events. And this is a typical graph that we get by diffusion entropy analysis. So this is the EEG with almost 10 to 5 data points, and on the right is the scaling. So this slope will give us a scaling. So scaling can be between 0 and 1. For a scaling of brain, usually we get something very close to 1. If a scaling is about 0.5, means the process is random, And scaling less than 0.5 is again complex, but not as complex as delta larger than 0.5. The problem is that when we are doing the experiment, usually the time series of EEGs are very short. For example, here, the participants rested for 3 minutes, like in this area, and for 1 minute, just 1 minute, they were doing the task of mental counting. And what we want to know, can we measure the scaling of this very short time? The good news is actually using diffusion entropy analysis, we can do that. So here is the very long time data points like 10, 7, 10 to 5. And on the right side is very shorter, so it's 3, 10 to 4 data points. And still we can have 1 or 2 decades of linear sections, means there's a scaling and we can measure that. Before going to the real data, I just wanted to create a surrogate data in a toy model to show this matching between the complexities is not something like normal. For that, I use a very simple agent-based model. So there are just 2 agents. I say agent 1 and 2. So, and they are playing a game which is a matching coin. Means the 2 agents have to show, each of them they have a coin, and in any trial they have to show to each other their coin. If the coins have same side, like both of them are tail or both of them are heads, one of them wins. If they are different, the other wins. So it's a competitive game. And of course, each of the agents will try to optimize its performance, its benefit. And to make a decision, there is a threshold 0, 1 for each agent, and each of them, they have this moving threshold. And to make a decision, it's very simple because each agent needs to create a random number. For example, if the threshold is here at this time and the random number falls here, this agent 1 will decide to show tail. For this other agent, imagine that it has to generate another random number, and imagine that falls even here too. So this one will decide to tail. So tail and tail. So now we know the decisions and they can see their payoffs. Imagine this one gets +1 and this gets -1. And now based on the payoffs, because this decision for agent 1 was good, we'll move the threshold a little bit to the right. So threshold will go to the right to improve the chance of picking tail for the next trial. And for this other agent, because it was bad decision, we'll move the threshold to the left to decrease the chance of tail. So now you can see this threshold for decisions will go back and forth, right? So it moves between 0 and 1. And here, the red is the position of that threshold. So it goes between 0 and 1. And you can see there is sort of oscillation. But this oscillation is emergent property of the process because they are competing. And if in the scaling, the other graph I just measured using diffusion entropy, the scaling of each piece. So I divide this trajectory to many small pieces, and for each piece I can evaluate the scaling. Then I can have the evolution of a scaling over time. And so you can see, like, whenever there is a knot, for example here, then the scaling is 0.5, means the threshold is in the middle, so it means that decisions are random. Then the scaling is, of course, very close to 0.5 here. So let's say here is 0.5. The thing is, with this very simple model, we have a process which creates a scaling which is complex. So the process is complex, but on top of that, the scaling changes over time. This was the trajectory of threshold of one system. So we had 2 agents. Now here I just showed the change over time of the scaling of both of the agents at the same time, and you can see whenever one of them has less scaling, the other will have the same. So when one of them behaves randomly, the other will behave randomly too. And when one of them is complex, the other will behave complex too. So there's a matching between the scaling of two processes. Means they have at each during the time they have same complexity. Now to the real data, this is the sort of data we have here, EEGs of a participant for 1 minute. And with diffusion entropy, we can go down to 30 seconds of analyzing the EEGs, the scalings. So this is the best data I have because it's the EEGs of patients with Parkinson's disease. So they embedded 8 electrodes inside the brain. So it's very clean data. And I just have the red curve shows when red curve is 1 means the patient is resting, and when it's 0 means that's a time that they ask the patient to open or close their fist. And the 8 curves are the scalings. You can see that there's a correspondence between the scaling and movement. So whenever the patient is at rest, the scaling is higher, versus when it's lower, they are moving their fist. So we cannot interpret this yet, but my point was that there is a corresponding, the scaling changes over time, and this happens inside the brain. The other data is more complicated because it's for the shooting task of participants. So they are looking in VR this scene and they have to shoot the enemies. So the task is go no task. And good thing about this data set is that they recorded EEGs, ECGs and respiration at the same time. That led us to measure the complexity of all these 3 different systems. So interconnected though. So the red is the scaling over time of ECG, and then the black one is for the scaling over time of the respiration data, and the rest are the EEGs for 64 EEGs, and there's you can see there's a synchronization between them. So means whenever the scaling of the EEG is lower, the scaling of ECGs and respiration is low too. And finally, this is the data for EEG of participant during doing the simulated driving task. And this is very clean data too. And over time, you can see that scaling of the participant based on the task they are doing changes. So it means brain is responding to the complexity of the task or what happens in their environment. So I conclude that using this, we can measure the complexity of short time series, about 30 seconds of EEGs, ECGs, and etc. And because of that, we can study the synchronization or connections between the complexity of interacting systems. Thank you.
Thank you for your talk. Yeah, I hope you can hear us.
Yes, I can.
So, any questions or comments? Just a second. I'm balloting around.
Hi, can you
Hello?
hear me? You hear me?
Yes, sure.
Okay, thank you for your presentation. It was very clear. And
Thank you.
I have a question. So this synchronization is achieved through diffusion entropy analysis, right?
Yes.
Okay, and regarding the ECG signal, you used RR series or the ECG?
No, so one way is to do that, but we do the same exact thing. So we take the time series and we define these thresholds, about 50 of these thresholds, and then we evaluate the events and we create the secondary time series. So the same way, I treated all of the data the same.
So you have not extract R peaks and then calculated
No.
the R series. Okay, so
No.
you use raw ECG signal. I mean, only pre-processed. I mean.
Yes, right.
Okay, and regarding the slides when you compare the respiration, EEG signal and ECG signal, I saw some differences in the amount of synchronization could it be related to the different, let's say, frequency of the signals? Because it seems something like that.
This is just preliminary results, and we are trying to find out like what that means. Yes, there are three different systems with very different frequencies, but the interesting part was actually that they have same complexity, different frequency, but same complexity.
Okay, thank you so much.
Thank you.